Okay, so for my linear electron geometry, I chose to do beryllium bromide, which is BBr2. And then beryllium has 2 valence electrons, bromide has 7, but then there's 2 of them, so you multiply by 2 and you get 14. When you add them together, you get 16 total valence electrons. And then you're going to put the least electronegative in the center, which will be beryllium. And then you add a bond and a bond, and then your bromides. And then that's 1, 2, 3, 4. You can take away from here, which leaves you with 12. So then you fill in the rest, and you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we use all of them, left with 0, which is good. And then from there, we can tell the shape. It's linear because there are no unpaired electrons on the center, which means that there's a 180-degree bond angle. And we can tell that it is nonpolar because it is symmetrical, and if it's symmetrical, it cannot be polar. Nonpolar. And since it has 2 electronic domains, its hybridization is sp. And then for the formal charges, for the bromides, we have 1, 2, 3, 4, 5, 6, 7, and it has 7, so cancels out. And then here we have 1, 2, awesome, and that's the formal charges. And then since the beryllium is more electronegative, we're gonna draw our dipole arrows like this. And then there. Okay, perfect. And then for my creation of this, I used foil, and the red one in the middle is the beryllium. These are the bromides. And yeah, it's linear, it's straight, symmetrical, nonpolar. And then for trigonal planar, I did sulfur trioxide, which is SO3. And for the valence electrons, sulfur has 6, oxygen has 6, but there's 3, so times 3. Add them together, 6 plus 18, 24. And then that's your total. So then you're going to put the least electronegative in the center, which is the sulfur, and then bond it to your oxygens. And so that's 1, 2, 3, 4, 5, 6. We have to take away, which leaves us with 18. I fill in the rest. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But with this one, we have to look at the formal charges. So the formal charges of oxygen is 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1 for all of the oxygens. And then for the sulfur, it's 1, 2, 3. 6 minus 3 is 3. And it's just not good to have formal charges of 3 and -1. So we can change that by making them double bonds. So we'll just add that there. Perfect. And then now if we look at our formal charges, there's 1, 2, 3, 4, 5, 6 zeros. And then on the sulfur, it's 1, 2, 3, 4, 5, 6 as well. So 0 for all of those. And then the oxygens are more electronegative, so we're going to draw these arrows, and it would go out to all the oxygens. And so that means that these would have that and this. Awesome. And then looking at this, you can tell that it would be a trigonal planar because there's no unbonded electrons, unpaired electrons around the sulfur. So they would be spread out evenly, which means it's trigonal planar. and that means the bond angle is 120 degrees, and it is symmetrical, so it's non-polar. And then the hybridization, there's 3 electronic domains. So the hybridization would be sp2. And then my diagram for this, there you go. And I just put these papers showing that there's a double bond on both of these, and the middle is the sulfur. Here's your oxygens. They're spread out evenly. And yeah, and for tetrahedral, I chose to do hydronium, which is H3O+. And then for H, for the valence electrons, we have 1 times 3 valence electrons. And then for the oxygen, we have 6, but then a -1, so we have 5, which gives us 8 total. So the oxygen has to go in the center because the hydrogens can't go in the center. So we have oxygen, hydrogen, hydrogen, hydrogen. So then we're just gonna look at this. So 1, 2, 3, 4, 5, 6. So that means we have 2 left. And they have to be bonded to the oxygen because the oxygen needs to be filled to the octet rule. So it would have 1, 2, 3, 4, 5, 6, 7, 8. And then since the oxygen is more electronegative, we draw our arrows like this coming from all the hydrogens. And then this would be that. That would be that. And then if we look at the formal charges, the formal charge of the hydrogen, and then the hydrogen, if we're finding the formal charge, it has 1 valence electron and 1 here. So that would give us 0. And then the oxygen has 6, and then right here it has 1, 2, 3, 4, 5. So its formal charge is 1. And looking at this, we can tell that it is a trigonal pyramid because it has 4 electronic domains, but one of them is unpaired electrons. So I remember that the bond angles are less than 109.5 degrees. And then this is non-symmetrical, and it has a polar covalent bond. So that is polar. And since it's hybridization, or the electronic domains, there's 4, the hybridization would be sp3. And then the diagram for this looks like this. They are bent down because there's an unpaired set of electrons up here, and they're all evenly spaced at the bottom. And yeah, and then for trigonal bipyramidal, I chose to do chlorine fluoride, which is ClF3. Chlorine has 7 valence electrons. Fluoride also has 7, but that's multiplied by 3. And we get 21. Add them together, we have 28. So as we can see, the chlorine is less electronegative. So we put it in the center, connect it to the fluorides. And then we have 1, 2, 3, 4, 5, 6. So -6, we have 22 valence electrons left. So then we fill it in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we still have 4 left, so we just have to add those on to the middle right there. And those will both be a set of unpaired electrons. And then from there, we can tell, we know that the fluorides are more electronegative, so we're going to draw our arrows. That means these would be like this, that would be like that. And then for our formal charges, 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. 0 for all the fluorines. And then the chlorine, we have 1, 2, 3, 4, 5, 6, 7. So that's also 0. And then based off of this, we can tell it is going to be a T shape because it has 5 electronic domains, but 2 of them are unpaired sets of electrons. And then bond angle is less than 109.5 degrees. This is also polar because it is non-symmetrical and does have a polar covalent bond. And its hybridization would be sp3d because there's 5 electronic domains, so 1, 2, 3, 4, 5. And then my example for this one is right here. It looks like this. And for this one, I created this. You can see that there's that T shape there. And then the 2 sets of the unpaired electrons are up there. So yeah. And then lastly, we have the octahedral. And for this, I chose to do selenium hexafluoride. So that's SeF6. And here we have 1, 2, 3, 4, 5, 6 valence electrons. Here we also have, 7 times 6, we get 42, and that adds up to 48. Awesome. And then, so since the selenium is the least electronegative, we're going to put that in the center. And then we have 6 fluorides. 1, 2, wait, how am I going to do that? 3, 4, 5, 6. Okay, awesome. And then we're going to add those right there. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Minus that from there. 36 left. So then we're going to add those on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So there we have used all of our valence electrons, which means we have 0. And so this would be an octahedral because it has 6 electronic domains and all of them are bonded, which means that all of these have a 90-degree bond angle with each other. And this is going to be nonpolar because it is symmetrical. And the hybridization will be sp3d2. And then if we look at our formal charges, 1, 2, 3, 4, 5, 6, 7. Minus 7, we get 0 for all the fluorines. And then for this one, we have 1, 2, 3, 4, 5, 6. Minus 6, we also get 0. And then the fluoride is more electronegative. So we're going to go like that. And this will have a plus charge. This will have a minus charge. And then for this one, I created this. If you look at it from the front, it looks like this. You have the 4 on the sides, and then these 2 are kind of added on. And the bond angle is 90 degrees. So, yeah.